Have you ever just looked around at everything, your desk, the air, even your own hand, and just wondered, what is all this stuff actually made of? Like, if you could just keep zooming in and in, what's the absolute smallest piece you'd find? Well, here's a fun way to think about it. It's kind of like a giant universe-sized box of Legos, right? You can build anything, a car, a spaceship, a whole city, but it all comes back to those same basic fundamental bricks. The universe, it works almost exactly the same way. So let's dive in and figure out what those ultimate building blocks really are. So that fundamental Lego brick we were talking about, the answer is the atom. And this isn't some brand new idea. Nope, this goes way, way back. I'm talking all the way to ancient Greece. See, there was this Greek philosopher, Democritus, and he coined the term atomos. And atomos literally means uncuttable, indivisible. And for more than 2,000 years, that was the thinking. This was it, the bottom of the barrel, the smallest thing you could possibly get. But of course, as you can probably guess, the story doesn't stop there. Yeah, it turns out the uncuttable can be cut. So let's do something those ancient philosophers could only dream of. Let's take a journey inside the atom. And this right here, this is the question that blew the doors off of modern science. If the atom isn't the end of the line, then what in the world is it made of? For something so fundamental, the basic layout is actually pretty straightforward. Right in the middle, you've got this dense, heavy core called the nucleus. And then you've got these super tiny particles called electrons just zipping around the outside, kind of like planets around a sun. Okay, so it really all comes down to just three main players in this little drama. Inside that nucleus, you've got two particles, the positively charged protons and the neutrons, which have no charge at all. They're neutral. These guys are the heavyweights. They make up pretty much all the atom's mass. And then whizzing around on the outside, those are the negatively charged electrons, which are, they're incredibly tiny and light in comparison. So you've got these three particles. How does that create everything? What makes an atom of, say, gold completely different from an atom of the oxygen you're breathing? Well, believe it or not, it all boils down to just one simple thing. The identity of any atom in the entire universe is decided by a single count: how many protons it has in its nucleus. That's it. That's the secret sauce. Take carbon, for instance. An atom of carbon always has 6 protons. It's non-negotiable. If you find an atom with 6 protons, it's carbon, period. But what if you add just one more proton? Now you have 7. Is it just a heavy version of carbon? Nope, it's not carbon at all anymore. It's a completely different element, nitrogen. That's how fundamental the proton count is. And this one simple rule, this is the secret behind maybe the most famous chart in all of science, the periodic table. Seriously, all it is a giant list of the elements, perfectly organized by the number of protons they have. We call that the atomic number. So hydrogen is number 1 because it has 1 proton. Helium is number 2, 2 protons, and on it goes. Okay, so protons define the element. Check. But what about those neutrons hanging out in the nucleus? Well, this is where things get really interesting. If you change the number of neutrons, you get a fascinating little variation we call an isotope. So what is an isotope? Simple. It's just an atom of an element that has the same number of protons, so it's still the same element, but it has a different number of neutrons. Same identity, different weight. This picture here is a perfect way to visualize it. Let's look at hydrogen. Hydrogen always has 1 proton, but it can have 0 neutrons or 1 neutron or even 2. In every single one of those cases, it's still hydrogen. But these different versions, these isotopes, we call them protium, deuterium, and tritium, they have different masses. They literally weigh a different amount. All right, so we've covered protons and neutrons. That just leaves those little electrons whizzing around the outside. Now, in a standard, everyday atom, the number of positive protons is perfectly balanced by the number of negative electrons, so the atom is electrically neutral. But what happens if that balance gets thrown off? Well, that's when you get something called an ion. An ion is just an atom that's no longer neutral. It's got an overall electrical charge, either positive or negative, because the number of electrons doesn't match the number of protons anymore. And they come in 2 main flavors. If an atom gains an extra electron or 2, it now has more negative charges than positive ones. We call that an anion. And if it loses an electron,
Well, now the positive protons outnumber the negative electrons, and we call that a cation.
Okay, let's put all this together. It's pop quiz time. We've talked about all three particles and what they do. So now, let's use what we've learned and see if we can decode this symbol right here.
So what we're looking at is an ion of something called chlorine-37. And just from these little numbers here, we can figure out everything about its structure. You ready? Let's do it.
Okay, let's break it down step by step. First up, protons. That's the easy one. It's always the atomic number, that number on the bottom left. So boom, 17 protons. Next, the neutrons. Okay, that number up top, the 37, that's the mass number. It tells us the total number of protons and neutrons combined. So to find just the neutrons, we take the total, 37, and subtract the protons we already know, which is 17. That leaves us with 20 neutrons. Easy enough. All right, last one, electrons. Now, if this were a neutral atom, it would have 17 electrons to balance the 17 protons. But see that little minus sign in the corner? That tells us it has a -1 charge. And how does it get a negative charge? By gaining an electron. So we take our starting point of 17, add 1, and we get 18 electrons. And there you go. 17 protons, 20 neutrons, and 18 electrons. We figured it all out.
And you know, that's really the mind-blowing part of all this. When you step back and think about it, everything you can see, everything you can touch, everything you are, it's all just different combinations of these three simple, tiny particles: protons, neutrons, and electrons. It makes you wonder, right? What other incredibly simple rules are out there, just hiding underneath all the complexity of the universe?